Hi students, welcome to CM3291, Advanced Experiments in Organic Chemistry and Inorganic Chemistry. I'm your lecturer for this experiment, Feng Fuman, and this experiment is about the synthesis and the resolution of a secondary alcohol towards the synthesis of Goniothalamin. Chiral resolution in stereochemistry is a process for the separation of racemic compounds into their enantiomeric form. It is a very important tool in the production of optically active drugs. There are other terms that has the same meaning as chiral resolution. Some people call it optical resolution, or you can call it mechanical resolution. We know that nature provides us with an unlimited source of natural products that exhibit interesting biological activities. The development of new compounds bearing various structural arrangements and remarkable properties stems mainly from these natural products. For instance, it has been shown that the sterile lactones, largely found in the genus Goniothalamus, exhibited remarkable anti-proliferative activity against cancer cells. The Goniothalamus family consists of about 115 species of shrubs and trees that grow mainly in Asia, and many of these plants are used as a source of fiber, as a repellent against mosquitoes, and especially in traditional medicine. For example, extracts of Goniothalamus ammuyon seeds are used to treat edema and rheumatism near the southern coast of Taiwan. The insignificant effects that these sterile lactones have on normal cells is well documented, which suggests that the cytotoxicity of the latter seems to be specifically target cancer cells. A substantial amount of evidence suggests that the anti-proliferative activity of sterile lactones is linked to the introduction of apoptosis in target cells. Now, the synthetic chemist today has a primary role to play in the development of new treatment by implementing efficient synthesis of these compounds and preparing unnatural analogues to optimize the biological activity. And this highlights the parts of the molecule necessary for biological activity in order to optimize them. So many efficient syntheses of such natural products and its analogues in this case have been reported in literature. So in the year 2004, Hansen and co-worker reported an interesting synthesis of both Goniothalamin enantiomers using a combination of lipase-catalyzed resolution and alkene metathesis. The synthesis began with the Grignard addition of allyl magnesium bromide to a trans-cinnamaldehyde to form homoallylic alcohol 3, which is under scheme 1, later you'll see that. Enzymatic kinetic resolution catalyzed by immobilized Candida antarctica lipase B, in short CALB, that will afford the ester 4, the R isomer. You can refer to this in your lab manual, it's all there. And we also have the unreacted alcohol 5, which is the S isomer. So the two products were separated using flash column chromatography, and then ester 4 undergoes metathesis reaction using Grubbs catalyst to afford the R Goniothalamin 1. So separately, alcohol 5 could be converted into S-Goniothalamin 2 via a two-step sequence, the esterification using acryloyl chloride and then ring closing metathesis. Now, it is interesting to note that the R enantiomer is the only molecule to be isolated from nature. And it turns out that it is a phenomenal drug discovery because scientists made that S isomer in the lab and found that the mamic one is so much more effective than R1. And because of this great efficacy of this molecule to the kidney cancer cell, there are numerous reports on the synthesis of both the R and the S isomer of Goniothalamin. So here in this reaction scheme, you will see that in your synthesis you will make two compounds, both the enantiomers of Goniothalamin. So we begin with the Grignard addition of trans-cinnamaldehyde and make a homoallylic alcohol. And in the second step, the racemic alcohol will be separated into its pure form, and in the process known as chiral resolution. Now, CALB is short for Candida antarctica lipase B. It is a lipid enzyme, and the reaction with a vinyl acrylate to form the R ester 4 and this is done by the trans-esterification method. Now this is known as trans-esterification because a new alcohol fraction replaces the original alcohol part of the ester. You see, it's an ester, and then this is the alcohol, so this alcohol replaces that alcohol to form a new ester. So the R isomer of molecule 3 will become an ester, while the S isomer will stay the way it is. So now we have different chemical and physical properties because they are totally different molecules. Now, following which, the R ester 4 will undergo ring closing metathesis, in short RCM, with Grubbs catalyst to give rise to the natural R form of Goniothalamin. And for the S alcohol 5, we will conduct an esterification with an acid chloride. In this case, we are using acryloyl chloride. So followed by applying the Grubbs catalyst here to form the next product, and then a ring closing metathesis mechanism to yield the S form of Goniothalamin. So this is really good synthesis in which both enantiomers are formed. And this is excellent because both isomers have great drug efficacy. You can't beat that. You know, sometimes in the drug market, one of these enantiomer is very harmful, where the other one is very effective. You know the case of history, thalidomide. It was so disastrous last time. Check it out. So here our objective for the synthesis is to achieve a very high enantiomeric excess of the alcohol. And so we want the dominant S enantiomer. So in week 1, we will apply the Grignard synthesis to make compound 3, and the second week, we will carry out the chiral resolution to separate the mixture into the S alcohol 5 and then the R ester. So take note, here we have the enzymatic kinetic resolution that may take more than 24 hours. So after we finish the Grignard synthesis, we should set up the next reaction, and in week 2, we will conduct the workup and the column chromatography. Take note of that. Now for this Grignard experiment, we will learn about the flame drying technique using the hot air gun, and also using the commercially available Grignard reagent. So there are two main objectives here. One is to learn about the flame drying technique, and the other one is to deal with moisture sensitive chemical reaction. So for the flame drying technique, we will be using the Schlenk line to execute the procedure, and we understand that the Grignard reagents are very moisture sensitive. So at the advanced level of chemistry lab module, we would like you and all of us here to adhere to a strict environment under nitrogen. So we need to connect the system to the two-way manifold of the Schlenk line. Now this is the Schlenk line, and note that for the normal, the valve is horizontal. Alright, so if the blue part of the valve points up, we are having a vacuum connected to our system, and if the blue part points down, we are connecting it to the nitrogen. Alright, take note, this legend is pasted at the back of the fume hood. Be clear. Anything not sure, please ask your lab technicians or the instructors, the lecturers in the lab. You should watch this video prior to entering the lab, because it will showcase to you both techniques using the flame drying hot air gun and also using the Schlenk line. Now, so for the flame drying process, we use the hot air gun here and blast heat to the glassware. So any vapor will be removed by vacuum suction. You see, go into it, rendering the system completely dry. And after that, we will refill the system with nitrogen source. It goes in, which provides for inner atmosphere. Now, so the entire Grignard reaction will be carried out in nitrogen, and there will not be air or moisture going into the system, which is very desired because it's Grignard reagent. As a safety precaution, since we are going to use the hot air gun, it's really hot. It can go up to 600 degrees Celsius. If you choose the wrong setting, we are using about 400 degrees Celsius, approximately there. So we need to ensure that there's completely no solvent or other chemicals inside the fume hood. Nothing at all when you're using the hot air gun. Also, you have to let the system cool down first to room temperature before you introduce nitrogen into the system. And this is extremely crucial because the Grignard reagent which we used has a very low boiling point, or you can say considerably low compared to other Grignard reagent. So you may click on this link to access the video guide on flame drying technique. Please do. We can see if you have viewed it. Now for the Grignard reaction, let's follow the procedure. So first, using needles, add trans-cinnamaldehyde 0.38 ml, 3 millimole, and anhydrous THF into the reaction flask. Cool the mixture in an ice water bath. Okay? Then, how do you handle the allyl magnesium bromide reagent? So you know that this bottle here will contain the allyl magnesium bromide, which is a 1 molar solution. Okay, next you need to clamp the bottle that was purchased using a retort stand, and then connect the bottle to a schlenk line via needle and place it under nitrogen. Of course, you have the adapter open to nitrogen, and then using a 10 ml syringe with a long needle, you see this long needle here, choose the right one, measure 6 ml of the solution, and before you withdraw the needle out of the bottle, draw some nitrogen into the syringe, because this will protect the solution and ensure that there's no dripping of your very reactive reagents there. And then add the allyl magnesium bromide dropwise into the cool reaction flask here. And once the reaction is completed, remove the ice bath and let the reaction stir at room temperature for 2 hours. You see, so the reaction is conducted at RTP, but during addition, we need to keep it very cold. We need to quench any leftover Grignard reagent that's hidden in the syringe or the needle with saturated ammonium chloride. So you're going to perform this step in the waste film hood. This is a diagram that I was saying about the procedure. You see the clamp here for both the bottle. This is sealed inside nitrogen gas. You're going to clamp the tubing as well that connects to nitrogen. Now, here we depict the use of a moisture-sensitive reagent, the allyl magnesium bromide, which is purchased commercially from the company here. Now, this is sealed under nitrogen and can be kept for a long period of time. So we note that every time we work with such chemicals, we always have to acquire the nitrogen atmosphere. And the schlenk line will be needed to connect the needles, right, first of all. And from the needle, it is inserted into the bottle, pumping nitrogen gas in. It is the utmost pertinent step as we are trying to withdraw the liquid from the sealed bottle. If you do not insert any nitrogen in, and if you're trying to pull out the liquid, we're going to make a small vacuum, right? It's going to be tremendously difficult. So that's why you need to secure the bottle with a clamp, right, with a retort stand. And since we need to reach out, so we should use a long needle. And to have a good practice, the syringe should be under nitrogen. Every part of this should be under nitrogen. That means before using it, the syringe and needle should be purged with nitrogen first. Everything moisture free. Now the allyl magnesium bromide should be added dropwise to the reaction flask. Why is it so? Think about it. You should discuss it with your friends. Brainstorm for the consequences if this is not done properly. And since we use a slight excess of the Grignard reagent, the reaction time is typically only 2 hours. So now, when we add the Grignard reagent, the reaction flask should be placed inside a ice bath, as the reaction is very exothermic and the massive heat involved is not dissipated quickly enough. It may decompose your compound. And after the addition, we need to remove the ice bath so that we can carry out the reaction itself at RTP, room temperature and pressure. And in the syringe and the needles, after usage, there might be trace amount of the residual Grignard reagents left. So to have a safe practice, we need to quench these materials. So please walk slowly into the waste, not into the waste, towards the waste film hood, and gather yourself calmly and quench it with, it's all there, saturated ammonium chloride. So you can read from the slide here. Now after 2 hours, right, when the reactions has finished, you disconnect the system from a Schlenk line, quench with desaturated ammonium chloride, and then perform standard extraction using ethyl acetate extraction. Remember, this is a technique that you have learned some time ago, maybe 2 years ago, 3 years ago. Extraction. You shake it. Do you remember? Now this reaction is quite efficient and clean and requires no purification. Happy? And we will characterize the product with the assistance of the product NMR. Now a note here is that in the product NMR, since there are a lot of CC double bonds present in this structure, there will be lots of vinyl peaks. And we might not be able to assign all of them. But try your best to. Try your best to assign them. Sometimes it's possible. Like always do your best in everything. Don't give up. Now for the reference of the data, you might wish to look up this synthesis paper on the slide given to you. And this paper will familiarize yourself with the background of this reaction. Suppose the reaction is not complete, or you ended prematurely. There may be some trans-cinnamyaldehyde left, which are visible in your NMR spectrum. You can tell. Next part will be the enzymatic kinetic resolution. After the Grignard reaction, there exist two enantiomeric forms. And recall that CM1121, we spoke about enantiomers having the same chemical and physical properties. So how do we separate them? How do we differentiate them? Could we use TLC to separate them? What do you think? So the two enantiomers would react uniquely in the presence of a chiral reagent. So here we introduce an enzyme catalyst. You know enzymes are chiral, and so the two enantiomers would react at a different rate, Kr and Ks. Who knows, maybe this reactant will Ks the other reactant. Our enzyme here is a lipase, which is intelligent enough to distinguish between the two enantiomers, thankfully. And it will cause one of them to react so much faster than the other one. So in this case, the R isomer reacts faster. So the Ks got Ks. Now this is a better picture for you to see. A and B, the different schemes. So this enzyme is actually asymmetrical. It is chiral itself, so both can function well, but which is better? You can tell from a diagram. A certainly is the best way to fit into the model. So that's the reason why one reacts so much faster than the other one. Now if the reaction proceeds partially, like midway, then most of the R isomer will be converted into the ester, and most of the S isomer remains as an alcohol. Understand? So since the products here are different, we have an ester versus an alcohol, so you can now separate them using the difference in the properties. And here we understand that the rate of the reaction for the S isomer is so much smaller than the R isomer. Alright, so here in this resolution scheme, you see that the R isomer would be worth 50% and the S isomer would be worth another 50%. And after going through the lipase-catalyzed reaction, you would have the R ester and a small amount of the S ester. Why small amount and not the dominant one? And the other side of the products, you get the S alcohol and a small amount of unreacted R alcohol. And since our major products here are the R ester and the S alcohol, and they have different functional group and structure, we can separate them using column chromatography. And in the products, the ester will be the one that has more of the R isomer, and the alcohol is the one that has more of the S isomer. So here in this case, we have what we call the enantio-enriched compounds. Now, if the Ks is 0 or very significantly compared to Kr, the small k here represents the rate constant for the selective process to convert the S isomer. What if it's very tiny? Then it means that the reaction will stop at exactly 50% conversion, because it's really too slow. It is like the rate determining step is so slow compared to the other one, so the other one will just proceed at a very, very fast rate. That means that the isolated products are pure R ester and the pure S alcohol. Now we have one question for you here. Which laboratory techniques allow us to monitor the reactions to stop it at 50% conversion? I believe you have learned this laboratory technique before. Have a discussion with your friends. Let us know. So the procedures for week 1 to set up. You should be able to prepare a dry 100 ml conical flask equipped with a quick fit adapter. You need to weigh about 0.174 grams of the green product, and because it is a liquid, you have to weigh directly into the flask through an electronic balance. And then inside the fume hood, you need to add magnetic stirrer, anhydrous hexane, vinyl acetate according to the lab manual for the mole ratio. And then next we add 0.13 grams of the lipase immobilized CALB and add it to the reaction mixture. When we say that the lipase is immobilized, it means that the active enzyme is coated onto the surface of the polymer so that it is more convenient to handle. So we just weigh this solid like a normal solid reagent. Okay. And normally for enzymes, because they are actually living materials, we store them in the freezer at about 0 degrees Celsius. So only during reaction time that we raise the temperature to ambience for it to react, so that it is now not inactivated. That means at ambient temperature it is activated. So after doing that, we fit a rubber atom to the conical flask and place the mixture in the incubator shader. Upon adding the enzyme, we need to seal the flask with a rubber septum. Do it carefully, make sure it's tight. And for enzymatic reaction, the temperature is typically at 30 degrees Celsius. For such reaction, we also employ the incubator shaker to swirl the reaction mixture constantly for a long time. And because this reaction takes a very long time, it's more than 1 day, you can't be in the lab for more than 24 hours. So we need something like a machine to do a constant swirling. I mean, normally if a reaction is worth only 10 minutes, you can do it by our hands, right? Or even an hour, you can use the magnetic stirrer. So because the reaction time here is long, we will do the workup in the next session. This device here may look very small to you, but it can actually house all the group's flask. So don't worry, please don't fight for space. There is enough space for all of us. Share. Now for week 2, when you come back for the workup, so first you need to filter the suspension through a short pad of select as a material, white material, or off-white, and rinse the flask with 10 ml of ethyl acetate. So this is actually similar to packing a flash column. We have this glassware that's hollow in the middle. We need to use a cotton wool to plug the end first, make sure there's no solid flowing through, and then we add the select materials, alright, to have a layer, a bed of select. And then we need to rinse it with some 10 ml ethyl acetate first to wet it. Then we put the suspension through and filter it. Okay, so after that, you get the filtrate and you transfer it into a dry 100 ml round bottom flask. Why is that so? We will need to remove this solvent. Remember, the solvent here is ethyl acetate, using the rotovap. At the same time, we have to perform TLC analysis using the 9:1 ratio hexane ethyl acetate as the eluent. You should think about why the ratio 9:1. I mean, this is what we tested. What if it is 20:1 or less drastic, 2:1? What happened? What do you expect to see on the TLC plate? If you're not sure, you can try in the lab and test, and then you can really see for yourself and learn from there. So since we are going to conduct a flash column, we need to use TLC analysis to gauge the eluent and the products there. Now one point to take note is, once we rotovap the combined liquid, we will have the crude product. Got it? Now take note that in this crude product, there is no vinyl acetate present. Why? We also have a question for you here, that is, how many spots do you expect to be on the TLC plate? 1, 2, 3, 4, 5? How many? Now for the crude mixture, we should have, if you think carefully, the alcohol, the ester, the excess vinyl acetate, and other byproducts. But just now I said that right after rotovap, there won't be any vinyl acetate, even though you added excess vinyl acetate. Sounds confusing, right? Read again, listen to me again, and think about why. Even though at the start we have excess vinyl acetate, but after rotovap, there is no vinyl acetate, or shouldn't have any more vinyl acetate. Why is that so? Okay? After which, for the crude, we will do a NMR analysis on the carbon. We'll do an NMR analysis using a proton of the crude to check what is the mole ratio between the alcohol and the ester here. Now the procedure for conducting the flash column, it is the same as last time. You know how to pack it. Maybe you need to remember. You can watch the videos that we have prepared for you to show you the way to pack it. Maybe it has been a while in year 1 or year 2. So esters typically they are less polar, so we'll conduct the column using a 2% ethyl acetate first so that we can run it faster. We check the fractions using TLC, right? And if we notice that the first spot has your product is out, right? Which means that if you see that your first spot has the ester, you know that okay, you may combine the spot that has you may combine the fraction that has a single spot, and these are your ester, and then you can change the polarity of the subsequent eluent inside the flash column afterwards so that you can flush out the rest of your products. Okay, so here you see that one TFC plate at the senior level, we can even fit in 6 or 7 spots because we are more experienced, and then we know that it's a line. But then for your case, if you're thinking that you need some time as a debutant, maybe for you like to have a practice, you could put 4 spots on a TLC plate and then try and practice, because in the research level normally you see people having 8, 10 spots on the same plate. Incredible, right? I mean, it sounds preposterous, but it happens. Practice makes perfect. Good practice makes perfect. After which, we will collect each compound separately. Make sure you do not mix fractions with more than 1 spot together, and then we remove the solvents using the rotovap. And since here we have the 2 products, the alcohol and the esters, and there are 2 different compounds, so they could be separated using the column chromatography. So remember, the products here are the esters, which contains more of the R isomer, and the alcohol, which contain more of the S isomer. So here the products are enantio-enriched compounds. We will then check the purity of the products using the proton NMR. And here, since our aim also includes the investigation of the efficiency of the enzymatic reaction, we will send the alcohol for chiral HPLC analysis. So at the end of the day, we need to submit the round bottom flask with the alcohol product, return the cleansed conical flask so that other group mates can use them later. Now, final question for you is, why vinyl acetate is a common choice of reagent for enzymatic kinetic resolution? And besides chiral HPLC, what other methods allows you to determine the ratio of the 2 enantiomers? Brainstorm and discuss with your friends and think about which answer is most logical. Brainstorm and discuss with your friends and think about which answers coming from your teammates the most logical. Then learn to elaborate and substantiate your argument. If you propose solution A and the person propose solution B, there must be a better one, unless of course it's the same solution. And if you propose something, you need to know how to explain to go with your stand. It's not just saying I think so without any elaboration. Then you cannot convince any other people. So you need to explain the reason. You need to be able to explain the reasons in full details. And to assist you in answering these questions, we suggest you to take a look at the compulsory readings. So go through them. The solutions might be found inside. It's really useful. So thank you very much for watching this e-lecture. My name is Funman. It's nice to have you here. Enjoy learning. Goodbye.